Okay, 3.6. Is marginals and differentials so marginals and differentials. Okay, so the marginal cost the marginal cost at x given by c prime of x. So the derivative we're going to call the marginal. Okay, c prime of x. Okay, is the approximate cost cost of the x plus 1th item. Think of it as like the next item. Okay. Okay, where we have c of x plus 1, the cost of the next item is approximately equal to the cost of the previous item plus the change in cost. Okay, plus c prime of x. Okay, so the marginal cost, okay, is the approximate cost of the marginal cost at x given by c prime of x. Okay. Okay, is an approximation of the change in cost. Okay, from the say 10th item to the 11th item. Basically, how much does it cost for me to produce the 11th item based on how much has it cost to produce the 10th item? Okay. So let's, okay, similarly, I'll just say similarly. Okay, the marginal revenue. Okay, at x, okay, so the marginal revenue at x is given by r prime of x, and the marginal profit at x is given by p prime of x. Okay. Which is equal to r prime of x minus c prime of x. That's kind of interesting. Cool. Okay, so let's talk about how much it costs to get to the next item. Okay, so number one, okay, the cost function of c of x is 62x squared plus 2,700 or 27,500. Okay, so we've got our variable cost and we've got our fixed cost. Okay, and then we have our revenue function, which we're going to say is x cubed minus 12x squared plus 40x plus 10. Okay. So first thing I want to work on is I want to find the total profit P of x. Find the total profit P of x. Okay, so P of x is equal to R of x minus C of x. Okay, and so we're going to plug this in. This is x cubed minus 12x squared plus 40x plus 10 minus 62x squared plus 27,500. Okay. Okay, so we've got x cubed minus 12x squared plus 40x plus 10 minus 62x squared minus 27,500. Let's combine like terms. Okay, that's a 12. Okay, so this is x cubed minus 74x squared. This is going to be plus 40x plus or minus what's 27,490. 90. Okay, so that's P of x. Okay, so that's my profit function. Okay. Okay, so B. Find the cost, revenue, and profit for 50 items. Okay, that is when x is equal to 50. Okay. Okay, find the cost, revenue, and profit for 50 items when x is equal to 50. Okay, so what's the cost? The cost of this thing of 50 is going to be, what was it, 62 x squared, so 62 times 50 squared minus 27,500. Okay, if I plug that into a calculator, I will get $182,500. That's the cost. What about the revenue? The revenue at 50 is just going to be equal to x cubed, right? So x cubed, so that's 50 cubed, minus 12 times 50 squared, plus 40 times 50, plus 10. If I plug that into a calculator, I should get 97,010. So 97,010. Okay, and then if I do my profit function, okay, well, that should really be my revenue minus my cost. So, but again, if we just use the function that we came out with, this is going to be 50 cubed minus 74 times 50 squared plus 40 times 50 minus 27,490, right? And that will come out to negative 85,490 as my profit. So I have a net loss here. Now, does that make sense that it would be this? Well, yeah, what happens if I take 97,010 and subtract off 182,500? Well, I get this negative result here. Okay, this is the revenue minus the cost. Okay, so it's cost me a lot more. I haven't made up my cost yet at 50 items. I got to sell a lot more than 50 items. Okay. Okay, so it says find the marginal profit, C. Find the marginal profit for 50 items. Okay. And the approximate profit on 51 items. Okay, so let's find the marginal profit. Okay, so the marginal profit is going to be equal to P prime of 50. Okay, that's the marginal profit. Okay, the marginal profit is the change in profit. So this is the change in profit at X. Okay, that's the marginal. The marginals are the change in profit at X. Okay, so I know how much profit I got at 50. It was this here. Okay, but I want to know how fast is that profit changing? Well, it should be going, you know, is it going to go up? Is it going to go down? You know, hopefully it goes up the more items that I sell. Okay, but who knows? Maybe it's going down. We'll see. Okay, so okay. So what's the marginal profit? This is how fast, or we'll say how much is the profit increasing or decreasing when 50 units are being produced. Okay, how much is the profit increasing or decreased when 50 units are being produced? Okay, so we just need to find out what's P prime of 50. Okay, so let's go back and see, well, what was P of X? Well, P of X is this guy, right? It's X cubed, so P of X is X cubed minus 74X squared plus 40X minus 27,490. Okay. And so what's P prime of X? Well, P prime of X is going to be 3X squared minus, bring the 2 down, that's 148X plus 40, and then this guy goes to 0, right? Plus 0. Okay, and so now what do I want to find? I want to find P prime of 50. Okay, plug in 50. So 3 times 50 squared minus 148 times 50 plus 40. If I plug that into a calculator, I get 140. So what does this tell me? This tells me that my profit is increasing at a rate of $140 per item when 50 units have been sold. Oh, okay. So what's the approximate profit here? What's the approximate profit? Well, at 51, P of 51, we could say is approximately P of 50 plus the change that we went up, the marginal. Okay, this is P of 50. Well, what was P of 50? We already figured that out. P of 50 was negative 85,490. Okay, and then what was the change? What was the change? How fast is this thing growing or decreasing? Well, it's changing $140, okay, per unit. Okay, and this is going to be approximately how much profit I make on the 51st item. Okay. Okay, so what is that approximately? Okay, P51. Okay, is approximately negative $85,350. Okay, so it's still negative, but it's but the debt that we owe is decreasing. Okay. the debt is decreasing. Okay, so at the 51st item, we owe less debt. Okay, so that's called, this is an approximate profit. Okay, this is called a marginal, and this is called the approximate profit. This is the marginal profit. Now the marginal will change depending upon where you are. Okay, again, if we have, say we have a curve that looks like this, our profit curve looks like this, the rate of change here is much steeper than the rate of change here. So it depends on where you are at, is dependent upon what your marginal is. Your marginal is the slope of that tangent line. Okay, so how fast you're changing is dependent upon where you're located. Okay. Okay, now why do we do this? Okay, why do we do this? Couldn't we just get P51 from the, yeah, we could. We could easily plug in the 51st one into our model, right? We could easily plug in P51 into this equation here. And if I did plug that in, I would get negative 85,273. I would get negative 85,273, which is the difference. I'm off by a little bit. I'm off by $77, positive $77. Okay, that's what I'm off by. That's my error. So why wouldn't we just plug in 51 and get 51? Why do we want to do all this whole approximation stuff? Okay, well, because often in business, we are not given, okay, formulas for C of X, R of X, or P of X. Okay, we just don't know. We don't know the formula. Okay, we just know that when I sold five items, I made this amount of money. When I sold 50 items, I made this amount of money. When I sold 2,700 items, I made this amount of money, and it cost me this amount. Okay, I have data points, but I don't necessarily have a function, right? You could say, hey, when I sold 5 units, I made $100, and when I sold, 10 units, I made, a little bit more, maybe 250 or 225, right? And then you're like, oh, well, what happens if you sold 50 units? Well, then I made a bunch more. And then you're like, well, it looks like this is the case, but I don't know what the function is. So function, who knows? Okay, what's the function? Okay, so who knows? Who knows what the function is? Okay. Okay, but what do we know? But we know information about the present. Okay, we know information about the present. Okay, so we could say that, okay, how do I, and the information about the present, which we'll call C of X, R of X, P of X, okay. Okay, this is how many items I have sold today. right? How many items, how much it's cost me to produce X items, how much it's cost me, how much I've gained in revenue on X items, and how much total profit I have in X items. Okay, I say P of X is equal to R of X minus C of X, right? Okay, however, to make a prediction about the future based on the present, okay, we use a marginal. We use a marginal. Okay, we use the marginal. We say, okay, how fast has it changed? How fast did that change? And how is that going to help us make a prediction, right? How does that help us make a prediction? Okay, because we can make predictions then about C of X plus 1. The next item is based on the previous item plus the derivative at that item. Okay. Okay. And when you think of the derivative, just think of how much to get to the next item. How much is it going to cost me to make the next item? Okay, how much is it going to cost me to make the next item? If I have these fixed costs and I don't have to worry about the variable costs, then to get the 51st item, well, I know how much that's going to cost me, so that just goes into that, and then that can give me the next item. So I say that this is an approximate. It's a good approximation. Okay. So that's the marginal. The derivative is the marginal. Remember that. Derivative is the marginal, and it helps me to predict the future. Okay. The derivative is the marginal, and it helps me to predict the future. Okay. Okay. So, for example, if I told you that it cost me today, that it cost me up to today to make 100 items, it cost me $1,000, and that it cost me, okay, that to go to the net to make the next item, it cost me $10 more, then I would say, okay, in order to get the 101th item, the cost of the 101th item, I would just add these together. It would be approximate. And I'd say, oh, approximately $1,010 is going to be the cost of the next item. Now, that may or may not be true, but it's a good predictive model to get to the next item. Okay, we can only predict one item at a time. Otherwise, we could veer way off in our predictions. Okay. Say this is where I'm at this year. Where might I be next year? Okay. Okay, so now I'm going to attempt to cover a very difficult topic. Hopefully your brains don't melt out of your faces. But anyway, we'll see what happens. If the melting of the faces occurs, like in the Raiders of the Lost Ark. Hey, you know what? Why? Because of COVID. Hashtag coping with COVID. That's why. That's my excuse right now. That's my excuse for everything. Coping with COVID. That's it. That's why. Okay. Coping with COVID. Eventually, my mom is going to let me out of my room. But it hasn't happened yet. So Still locked in the same stupid room since March. Doesn't get it. Okay, she thinks that everybody's gonna die or something. I don't know. Go cough on her so that I can get my freedom again. Crazy lady. Crazy. You're a crazy lady. Yes. Thank you for sharing, Captain Random. Okay. Anyway, let's move on. Let the brain melting commence. Okay. So triangle X means delta X. Okay, this is delta X. Delta X. Okay. Delta X represents, okay, the change in X. Okay, that's how much my X values change. Okay, is delta X. Okay, from the difference quotient, okay, from the difference quotient, excuse me, I'm already coughing. See? Mom, come here. Okay. Okay, stop. Stop coughing. Okay, from the difference quotient, I'm down to 10 packs a day. Just kidding. Okay, stop it. Off the chain thing. Okay, delta X represents the change in X. Okay, from the difference quotient, we get, okay, f of x2 minus f of x1 all over x2 minus x1 is equal to the change in y values over the change in x values. Just think of this as the slope. Okay, slope between 2 points. Okay. Okay, so let's draw a diagram here. Okay, say I've got this curve, and I've got a couple of points here on the curve here. Okay, and we're going to call this, okay, x1, and we're going to call this x2. Okay, so from x1 to x2. Okay, now what we're going to do here is we're going to say that the secant line, I'm going to mess this up if I don't use a ruler. Okay, get back here. Get back to the rulers. Where's my ruler? Where's my ruler? There it is. Okay, there's my ruler. No. Right there. Okay. Let's say boom. Boom. Okay, so this is going to be, okay, the this distance here, we're going to call delta y. That's the change in y. Okay, that's delta y. Okay, this distance here, oops, this distance here, we're going to call delta x. Maybe I should put this in a different color. Call this distance here delta x. Delta x. Okay, and this guy, okay, this distance here, we're going to call that delta y. Delta y. Okay, so change delta x delta y, okay? Okay, so let's move that out of the way there. Okay, so, okay, this implies, that, oops, I won't do that far. There we go. This implies that, okay, that x2 is equal to x1 plus delta x, okay? So that's, the change in x is, well, the change in x is x2 minus x1. So if x2 minus x1 equals delta x, then x2 is equal to x1 plus delta x. So I can rewrite this, okay, there's a method to the madness here, as x2 is x1 plus delta x minus f of x1 all over, okay, x2, which is x1 plus delta x minus x1, and the x1's cancel. Okay. And so this is equal to delta y over delta x. Now, that makes sense that delta x is on the bottom, but now we can relate what delta y is. What is delta y? Well, delta y, okay, is equal to, okay, f of x1 plus delta x minus f of x1. Okay. 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 And so what I'm going to claim here, let's write this for delta x to what? Delta y. Okay. Delta y. Okay. What I'm going to claim here is that if I were to take a derivative, okay, at x1, so we'll say f prime of x1, okay, which I'm going to call dy dx, okay, dy dx or dy dx1, I guess, I don't know how we want to think about it, okay, okay, dy dx1, right? Okay, that my claim is that this, okay, is approximately, equal to delta y over delta x for small delta x. So for small delta x, okay? So here's the deal here, okay? So what I'm going to do is I'm going to take the derivative at x1. And what is the derivative at x1? I'm going to put this in black. The derivative at x1, okay, the derivative at x1 is going to be the slope of this tangent line. Okay, it's the slope of this tangent line. So there's the tangent line. This is, we're going to call that f prime of x. Okay, and what I'm going to do is I'm just going to, instead of this being x1, I'm just going to call this x. Okay, and that f prime of x, boom, okay. And then you can let x2 be something else, okay? Really doesn't matter. X2 is just kind of a dummy variable anyway. And so I can change this x1 to x. So, and I'm going to do that. I'm just going to get rid of the 1 here. Okay, so I'm going to say, hey, you know what? The idea is that for very small delta x, very small changes in x, the derivative will be approximately the secant line, the slope of the secant line will be approximately the slope of the tangent line. That's really what it's saying here. Is that, get rid of that 1 as well, okay? Is that for small changes in x, the slope of the secant line which is delta y over delta x, that's the secant line, okay, will be close to the slope of the tangent line, which I would call f prime of x or dy dx. Okay. Now, dy is called the differential of y, and dx is called the differential of x. Okay. Okay. And what we do is we say that dx is approximately, or is basically equal to, delta x. Okay, we're going to say that dx is equal to delta x. That's the differential of x. Okay. And if we do that, okay, and we let that be equal to that, then we can say that delta y, which we said was equal to f of x plus delta x minus f of x, okay, well, this is approximately, okay, well, how do I want to do this? Let's not do that. I want to say this. I want to go back to the diagram and kind of show you exactly what's happening here. Okay, this guy, okay, this guy here in black, this length is called dy. That's the differential of y. That's how much I'm going up on the slope of that tangent line. Well, how much did I go over? Well, I went over delta x. It didn't change here. Delta x was delta x. But there's a difference between how much I went up on the tangent line versus how much I go up on the secant line. Delta y is not equal to dy for large values of x, but it's going to be close. It's a good approximation if delta x is small. If delta x is big, then that error just keeps growing and growing and growing. Okay, it doesn't look like it in my diagram. However, if I were to zoom in on my diagram, say that I were to zoom in on my diagram here, and get this thing to right. Okay, and I were to zoom in right at x here, and we were to just kind of zoom in here. Oops. I'm going to zoom in right at x. Okay, I'm going to zoom in right at x. Okay, and now let's say that delta x is really small. So here's x, and the change in x is really small. Really small, just bloop right there. Okay, this is delta x now. Okay, delta x. We zoomed in, and so delta x is really small this time. And so what do we know? We notice that, well, there's not much difference in the secant line, the dy and the delta y. There's not much difference in the slope of the secant line versus the slope of the tangent line. Slope of the tangent line is right there. I mean, it's really hard to draw because they're just so darn close. Okay, so I'll use a different color here. Okay, the tangent line approximates the secant line extremely well when delta x is small. for a small delta x. And so what we can say, okay, what we can say based on this thing here, okay, is that, okay, f prime of x, which is equal to dy dx, okay, which we would say is approximately delta y over delta x, okay, and so, okay, actually, you know what, I'm not even going to say that. I'm just going to solve for dy in this case. Okay, I'm going to multiply both sides by dx. Okay, and I'm going to say dy. This is hard to see. Let me make that a little bolder. Okay, dy is equal to f prime of x dx. Okay, and so what is dy? Well, dy is equal to f prime of x. But what did we say dx was? We said dx was delta x. This is delta x. Okay, and you're like, that's great, Professor Holtman, but who cares? Right? Okay, so all you need to know is that this thing, okay, approximates the change in x. Okay, and this thing approximates the change in y. Okay, and this is the differential of x. Okay, differential of x. Okay, and this guy is the differential of y. Okay. So dx is equal to delta x, dy is equal to f prime delta x. Okay. Okay, so maybe we'll forego the history of math lesson here. But once again, okay, what is dx? Dx is equal to delta x, and dy is equal to f prime of x delta x. Okay, that's what we need to know here. Okay, so do we do an example? No, not really. Oh, yeah, we did. We're on number 2. Okay, so number 2. Number 2 says something. Okay. Okay. Oh, note. Let's do a note here. Note. Okay. Okay. dy dx equals f prime of x is the derivative of y. Okay. The derivative of y. Whereas dy equal to f prime of x delta x is the differential. So just don't get that confused. Don't get the derivative and the differential confused. Okay. That's the differential of y. Okay, what's the difference? Well, the difference is that the derivative is dy dx. It's dy over dx. The differential is just dy by itself. Dy equals to f prime of x delta x. Okay, so this one's by itself, this one's over x, and that's the derivative. Okay, and it's a dx, not a delta x. Okay, but we said that dx was equal to delta x, so keep that in mind too. Okay, Just note these, okay? Okay, there. There's a little, this is the secret. Okay, this is the secret. Okay, so there you go. Okay. This is the secret. Okay, that's a secret too. Okay, just let you know. Okay, so number 2 here. Okay, so it's okay. It's okay. You know why? Hashtag coping with COVID. That's it. That's why. Okay. Hashtag coping with COVID. It's all good. It's all good. Okay, given f of x equals the square root of x equals 9, and dx is equal to 1, calculate, okay, dy and delta y. Okay, cool. Okay, dy and delta y. Okay, nice. Okay, so what was okay, so what's dy? dy is equal to f prime of x delta x. Okay, so what's delta x equal to in this case? What's delta x equal to? Any ideas? Delta x. What's the secret? What's the secret? Oh, this is a secret. The secret is that dx is equal to delta x. Exactly. Thank you, Darlene. Darlene knows the secret. Boom. There you go. Oh, just like that. Okay. So delta x is equal to 1. Okay. What's f prime of x? What's f prime of x? Okay, well, I don't know. What is f prime of x? Well, that's the derivative, right? So if f of x equals radical x, what's f prime of x? Isn't that 1 over 2 radical x? Right? So what's dy here? Well, dy is equal to f prime of x. Well, what is x? X is 9. So this is going to be 1 over 2 radical 9 times dy, which is delta y, or sorry, times delta x, which is 1. So this is the square root of 3, right? Oh, 1 over 2 times the square root of 3 is 1 over 6 times 1 is 1 over 6. So that's dy. dy is equal to 1/6, which equals 0.166 forever. Okay, so that's dy. Okay, so that's the differential. This is the differential. Okay, what's the change in y here? What's the change in y? Well, the change in y, okay, over the change in x is equal to what? F of x2 minus f of x1 all over x2 minus x1. Okay, so what's this guy? What's the change in y? Well, the change in y is just the top here. Oh, okay. What do we say x2 was? We said f of x2 was x1 plus delta x, okay, minus f of x1. That's delta y, or we said that, hey, you know what? What's delta y? Delta y is equal to f of x plus delta x minus f of x. Okay, so that's delta y. Okay. Okay, so what is this? What's this going to be? This is delta y is equal to, okay, f of x. But what is x? It's 9. Plus, what's this guy? This is the differential, which is, or sorry, the the differential of x, which is the change in x. Okay, so this is the change in x, which is 1. Okay, minus f of what? F of 9, right? So we're going to actually do, well, this is going to be f of 10 minus f of 9. That's the difference, or the change in y. This is the change in y, the difference in y. Okay, this is going up 1. Okay, which is equal to, this is going to be the square root of 10 minus the square root of 9, because that was the original function, right? It was the square root function. Square root of 10 minus the square root of 9. If I were to plug that into a calculator, okay, 10 square root, 10 square root minus 9 square root, well, square root of 9 is 3. I get 0.162277, so 0.162277, okay, 67. And if I were to look at this, what was delta y? It was this. What was delta x? What was dy? dy was equal to 0.1666 forever. 166666666 forever. And so what's the difference here? What's the error? What's the error between dy and dx, or dy and delta x, or delta y, sorry. dy and delta y. I'll just subtract the two, and I get the error to be 0.004, and I'll just round it there. Okay, about 0.00. So very close. So very close. dy and delta y are very close, okay, for this function. Well, what does this function look like? What does this function look like? Well, it looks like this. It's a square root function. And so at 1, we're at 1. 1, 1. At 2, we're at radical 2. Right? We're at radical 2. So 1.4 something. Okay, so radical 2, radical 1. Right? Okay, that's what that looks like. Okay, and it's saying what? It's saying that the change in y with respect to the derivative, the change in y with respect to the derivative, what's the derivative? It's the slope of this tangent line. Okay, the change in y with respect to the derivative, that's dy, is very similar to the change in y with respect to the secant, which is delta y. Okay, what's the secant? It's right here. Maybe I should have used a different color. Okay, maybe even a different color. Let's use red, deep red, dark red. The lady in red is dancing with me, cheek to cheek. Okay, and so, oh, look at that. What's this distance here? Oh, that distance, that is delta y. That's the change in y of the secant line. And what I'm saying is, those aren't too far off. Okay, what's this little itty bitty piece over here? I'll put it in gray. Okay, this little itty bitty piece over there is 0.004. Okay? So they're both really good approximations of each other. Okay, so sometimes it's easier to take a derivative than it is to do subtraction. Sometimes it's easier to do subtraction than it is to take a derivative. So that's the moral of that story. Like, well, that's okay. Okay, so why do we even care? Well, let's do an example of this. Okay, let's find a reason to care, shall we? Oh yes, we shall. Okay. Exactly. School's in session. Someone's gonna be taught a lesson. All I have to say. Okay. Okay, let's do a business cost and tolerance. Okay, business cost and tolerance. Okay, let's do an application, a business application. Thanks. Thank you, sir. Okay. Okay. In preparation for laying new tile, Michelle, I don't know who Michelle is, but she's laying tile. Michelle, my belle. Something in French. Okay. Michelle measures. Okay, measures the floor of a banquet hall. Measures the floor of a banquet hall. And finds it to be square. Okay, so that's finds it to be square. So yes, it's a square banquet hall. This is amazing. We've got a banquet hall, we've got Michelle, we've got her lying a tile floor. I mean, what more would you want to be doing on a Tuesday night with your life than learning about this? I started telling jokes when I had to teach algebra to high school students, because otherwise I was going to become a very depressed person. I was like, you know what? I'm just going to tell jokes to lighten the mood, and it helped. It helped lighten my mood, because you know why? Because you know what? Teaching algebra to high school students, the algebra is not very exciting. That shit is boring. I just let you know. And so, yeah, it's like, and so I had to figure out again a way to make it to survive without them hating me. Exactly. Like, I was just like, just stop throwing things at my face. Okay? Please. I'll tell you a joke if you just stop throwing things at my face. Okay? I got tired of trying to duck. Okay? The older you get, you don't have as fast reflexes anymore. It's like whoosh, whoosh, whoosh. Right? You just don't. You don't got the fast reflexes. What is today? Today is Tuesday? Is that right? Oh my gosh, today is Tuesday. Why does it always already feel like Thursday? Exactly. So it's Tuesday, and we're getting through. Okay, that's good. Okay, so yeah, it's Tuesday. So I had to pick up some skills along the way. I went to Disney, to downtown Disney over the weekend, because I was not coping real well on Saturday. I called my daughter on her phone. We just call each other. I'm like, why get out of your seat if you just want to talk to somebody in the next room? You just call them on your phone, right? Doesn't everybody do that? Like, hello.
Despise it. I despise it.
Yeah, exactly. It's like, hello. You know, you're laying in bed. I'm like, I'm too lazy to get up. I'm just gonna call her, right? I call her, and I said, hey, do you want to go to downtown Disney with me, right? And she says, yes, because we're both Disney freaks. And so she's like, yes, I want to go to downtown Disney with you. Okay, so we went in downtown Disney. We stood in like maybe an hour and a half line to get our temperature checked It was fine. It was good. It's good times. I mean, you go to you go to Disney, anything Disney, and you're gonna stand in line, right? It's like that just comes with the territory. And so then we're just like, okay, we're having a good time at Disney. And then I had to go and I had to purchase some of the Disney merch, right? So I had to get my, every time I go, I gotta get another one of these. Let me go. You stay right there. Okay, don't not go anywhere. You're gonna make it worth your while here. Okay, just stay. I saw you move, Maria. Maria, could you get back in your seat, please? Thank you very much. Stay. Okay. Here you go. So I had to pick, look at that. I had to pick up a new one of these because I keep breaking these damn things. I hit my children with them and they break. Exactly. Boom. Boom. Right?
Why don't you buy the younger version?
So, right. Then I was like, oh, I gotta kind of practice with my saber here, with my skills. So that's what I had to do. Don't buy the real. Yeah, exactly. I don't. You buy the cheap ones because then you can beat up your children with them. Exactly. Oh. So, I have a real one, like not a real one, like I want a real one. I want one that's made out of plasma. Okay, but I have one up on my shelf that's a better one. So, yeah. This one has actually given to me. This was given to me as a gift. This one's like metal and everything. So this is given to me as a gift. Okay. It doesn't do stuff. So yeah, the balance is off on this one. So. But this one's like $200. I did not pay $200 for this. I'm just letting you know. I let somebody else pay $200 for this and then give it to me. So that was how that one worked. So I'm like, pay $200 for a lightsaber. What are you, crazy? Anyway, so I like playing with the cheap ones. They're actually balanced better than the more expensive ones. So, and I've taught my daughter all the skills too. So we do like little exhibitions. We did a little exhibition of our skills there at the at Downtown Disney. We're just playing around, you know. I sent my wife the the video of us, you know, dueling there in Downtown Disney. So she was not. I don't maybe it's on my daughter's phone, probably. Is it called a photo drop type of thing? Who knows? Anyway. Again, why am I telling you this? Because this shit is boring. That's why. Who knows? I mean, I get bored sometimes. Okay, I'm sorry. We'll get back to Michelle. Don't worry. Michelle's not going to get neglected. Okay, I assure you. It's all good. Okay, it's all good. Okay. So, nope. 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 Nope, I don't. It's not. Okay. Anyway. Oh yeah. This is boom. Anyway. Okay. So. Oh Oh yeah, my daughter. I taught her all the skills too. So she had to get a new one too. She got a blue one, so that was fine. So anyway, COVID killed Disney. COVID has killed Disney. It's very sad. Okay. Okay, in preparation for laying new tile, Michelle measures the floor of a banquet hall and finds it to be square. Okay, measuring, ooh, that's good. We got measurements here. Measuring 100 feet by 100 feet. Okay. Suppose these measurements are accurate to plus or minus 0.5 feet. Okay, 0.5 feet. And we call this the tolerance. Tolerance. Okay, tolerance. Okay, so A, use a differential to estimate the difference in area due to the tolerance. Okay, due to the tolerance. Okay. So, what's the area going to be? Well, if it's a square, it's going to be x by x. So we're going to say that the area in terms of x is x squared. It's x squared. Okay. So now I'm going to take the derivative of this thing. Okay. This is going to be dA dx is equal to 2x. Okay. That's the derivative. Okay. Okay, and so I'm going to say that dA is equal to 2x times dx. Okay, nice, nice, nice. Okay, and so what is x? Well, we're concerned about what's happening when this is 100 by 100, right? 100 by 100. So I'm going to let x equal 100. And so dA is going to be 2 times 100. And what's dx? Well, dx is the change, is the delta x. dx is delta x, which is the change in x. Well, how much is x changing? Well, that's the tolerance. The tolerance is how much x is changing, and it's changing by plus or minus 0.5. So this is 200 times plus or minus 0.5, right? Yep. Okay, so what's the change in area? Well, the change in area is approximately 200 times plus or minus, that's plus or minus 100 square feet. That's a lot. Okay, that's plus or minus 100 square feet. Okay, now, is that a lot? Well, think of it like this. Well, what is the area? What's the area when x is 100? What's a of 100? Well, isn't that 100 squared? Which is basically, what, 10,000? So we're saying that this is already 10,000 square feet plus or minus 100 square feet. That's how much the area is changing. Okay. Okay, let's okay, I'm gonna intro 3.7. I may not get through the whole thing today, but I'm gonna intro it. 3.7. Yeah, maybe next time I'll show you the video of us doing our choreographed lightsaber show for all the people in downtown Disney to watch. So I sent my wife the video of me and my daughter with our choreographed lightsaber show. She sent a video back with her head like shaking and just saying, I married a child. Yeah. So, I don't know. At least I got a job, bro. At least I got a job. Okay. So 3.7. Exactly. Okay. 3.7. Elasticity of demand. Okay, elasticity of demand. Okay, what is elasticity of demand? Elasticity of demand is the measure of the sensitivity of demand to a small percent increase a small percent increase in price, okay? And that's elasticity of demand. Elasticity of demand, the measure of the sensitivity of demand to a small percent increase in price, I'll say is called elasticity of demand. Is called elasticity of demand. Okay, it's basically how sensitive is demand to changes in price, right? And then here's where I get to talk about milk and I get to talk about Starbucks. Okay, Starbucks versus milk. Starbucks versus milk. You have your $3 chai latte and you have your $3 gallon of milk, right? And those two beverages do not necessarily behave the same way. One is inelastic and one is elastic. Okay, and again, this is going to be part one of a part two series. Okay, so come back on Thursday to make sure that you catch part two as well. But we're going to intro it today. Okay? Well, my goal is to get at least to the formula. We'll get to the formula and then we'll use it on Thursday. Okay, so 3.7, there's going to be a part one and a part two. Okay. Let's say that a product has a demand function, and demand functions usually decrease. Why is that? Why do demand functions usually go down? Any ideas?
Because as prices, as prices decrease, demand tends to increase because people are willing to buy at lower prices.
Exactly, and vice versa is usually how people describe it. As price increases, what happens to demand?
It decreases.
Yeah, exactly. So usually demand functions are inverse relationships. Okay, as price goes up, demand goes down. Okay, let's say the product has a demand function that looks like this. It looks like d of x is equal to 120 minus 20x. Okay, so this is a line that starts at 120 and it goes down with a slope of -2. Okay, so this guy looks like this. Boom. Okay, right? So we're just saying, look, nobody's going to pay $60 for a cup of coffee, okay? Except for, people who are incredibly insane. Does that make sense? Like, right? So at $1, or well, maybe we'll make this $3. At $3 a cup for a cup of coffee, okay, you're going to get, I don't know, 100 and some odd, people walking into your store that day, right? So you'd be like, oh, I'm going to get 100 people demanding a $3 cup of coffee. Oh, okay, exactly. Okay, so $60 for a cup of coffee, forget it. Okay, I don't know. Better come out of like a monkey's butt or something. I don't know. Okay, so that was kind of gross. I apologize for what I said there. Okay, so I just apologize. Okay, so I blame COVID. I'm just blaming COVID. Okay, that's my catch-all right now. I'm just like, I'm blaming COVID. Like, what was it? 10 years ago, I'd just be like, I'm blaming Obama. 3 years ago, I'm blaming Trump. Now I just blame COVID. I don't have anybody to blame except for COVID. So it's like, hey, I'm just going to blame COVID. So exactly, just blame COVID. Okay. You gotta have some sort of scapegoat in your life. Okay. Okay. Where what? Where? Okay, X. Okay, X is the price per unit. Okay, that's where X is. X is the price per unit. Okay, and D of X is the quantity that will be sold. And D of X, it's D of X here, is the quantity sold. Okay, so if I take and I plug into this equation $2, okay, $2, okay, then I get 80 units per day, 80 units. Okay, 80 units. At $2, I'm making 80 units. Okay, 80 units. If I plug into this $2.20, okay, I'm gonna sell 76 units. Okay, so this is a 20-cent increase in price. Leads to, okay, it leads to what? Well, it leads to I go up 4, okay, actually I go down 4, sorry. Leads to 4 out of 80, 4 out of 80, which is a 5%, so a 20-cent increase in price leads to a 5% decrease in sales. That makes sense. 5% decrease in sales. Okay, cool. Okay, so right, so this is a 10% increase. Let me put 10% increase. So a 10% increase in price here led to a 5% decrease in sales. However, if I'm way out here, okay, then it becomes a different relationship. Okay. So if I say that, oh, instead of $2, I'm selling $4 coffee, okay, now the price goes up to $4, okay, that means that I'm only going to be selling 40 units per day. It drops by half. 40 units per day. I'm only selling 40 units per day, but I increase this by 10%, a 10% increase in price. Okay, let's increase this by 10% again. And now it goes down, okay, to 32, only 32 units per day. So that was 8 over 40, or a 20% decrease in sales. So this is 8 over 40. It's a much bigger difference, okay? So 8 over 40, which is a 20% decrease in sales. Okay, so notice that this 10% increase in price only led to a 5% decrease in sales. Okay, whereas a 10% increase in price here at a different part of the demand curve led to a 20% decrease in sales. This 40 cents had a lot more impact than this 20 cents. Does that make sense? Okay, that $2.20, that 20-cent increase had a lot bigger impact. I'm sorry, had a lot less impact. The 20 cents increase on my gallon of milk had a lot less impact than the 40-cent increase on my soy latte. And not a soy boy, okay? No matter what you heard. It's not true. Okay? We'll take whole milk, straight up whole milk, okay? I funnel it. I funnel the whole milk into my latte. Okay? That's it. Keep it spicy. Okay. So, okay, for example, okay, I think we're almost out of time anyway. Okay, I'll try to. When I have 80 units, say that I have 80 units here, right? At $2, how much money did I pull in? How much revenue is this? This is 160 bucks a day, right? Whereas 76 times 220, that's 167.20. Okay, that's 167.20, yeah. So that's a difference in $7, okay? So what happened? Well, even though I decreased the number of, okay, even though I decreased the number of people buying, I actually made more money here, right? This was an increase. This was an increase in revenue. What happened over here? What happened over here? What's 40 times 4? What is that? That's, oh, look at that. That's still 160. Oh, okay. So I still walked away with 160 in my pocket, right? So say that this is, you know, a grocery store selling milk at $2 a gallon. And I go up 20 cents. If I raise the price 20 cents, less people are going to buy the milk. But at the end of the day, I ended up making more money. Okay, I ended up making more money. Okay, whereas here, if I increase the price of my soy latte, okay, by 40 cents, 10% increase, I actually go down. Okay, I go down by how much money? Well, what's 32 times 440? 32 times 440, that's $140.80. I lose almost 20 bucks. Does that make sense? Okay, so let me write this down. Let's see what this is. So the demand at $2 was 80, and the revenue at $2 was 160. The demand at 220 was 76, but the revenue at 220 was 167.20. So that actually went up. Revenue went up. Okay, increase. Okay, whereas the demand at $4 is 40, so I'm still making a revenue at 4 of 160, but the demand at 440 There's 32, so significantly less comparative. Okay, comparative, we lose 4 people over here, but we still make more money because the difference is recuperated in those four, the difference of the 4 people is recuperated in the increase in the price for the other 76. I'm charging 76 people an extra 20 cents, and that's going to make up for the four people that I lost. Whereas here, I'm charging people, and I'm only charging 32 people an extra 40 cents, and that is not going to make up for the 8 people that I lost because I was already half as many customers. I already had half as many people. So this is R of 4.40, which is 140.80. This is a decrease. Okay. And so we say that the ratio of the percent change in quantity sold to the percent change in price is called the elasticity of demand, okay, and can be calculated as E of x is equal to negative x times d prime of x, that's the derivative of the demand curve, at x, at a certain quantity sold, or sorry, at a certain price point. So x is the price point. Okay, over d of x, this is the quantity. Okay, so the ratio of price over quantity, okay, times the rate of change, and then we take a negative. And the reason we take a negative here is because the rate of change is always negative for a demand curve. If you're going downhill, d prime of x here is always a negative number. So in order to make the elasticity a positive number, we multiply it by a negative. Does that make sense? You're always going to be going downhill. And so if you take the derivative of this, it's always going to be a negative slope. Okay, and so this ends up being a positive because the derivative of the demand. So this is the ratio. This is the ratio of what? This is the ratio of price to quantity as a function of how fast this thing is decreasing. How fast is it going down at that value of x? Okay, now. Okay, on Thursday, we're gonna figure out, well, what is this number, what does this value mean? Okay, and one of the things that we're gonna find, okay, is things that are called inelastic and things that are called elastic. Okay, typically more essential items have inelastic demands. So you remember going back to this milk here, right? Because the revenue increases, we say this is inelastic. Inelastic. Which means the market, the demand doesn't fluctuate as much for my gallon of milk. However, okay, when there's a decrease in revenue, maybe I should go over here. Okay. So this is inelastic. I don't know why I keep messing this up. Inelastic. Okay, that means that demand is not affected as much by a change in price. Okay, whereas this guy, which has a decrease, is called elastic. Wait, I think that's reversed. Typically, essential items have inelastic demands. No, that's correct. And luxurious items have elastic demands. No, that's right. This is right. Elastic. Okay. Elastic is where the demand is affected much by change in price. Okay. So this is how an essential item works, and these are how more luxurious items work. Okay, as soon as I start pushing my cup of coffee up, you know, to $5 for a cup of coffee, I'm gonna lose a lot more than if I were to push that gallon of milk from $1 to $2, right? So to pushing that latte from $4 to $5, bad idea. Okay, that's a bad idea. Because people can go without the coffee, or at least some people can. Okay, but going without your gallon of milk, taking that from $1 to $3, you're not going to lose as many people. Okay, it has a much more inelastic demand than the other one. Coffee is essential, exactly. Okay, priorities. Okay, I'm going to stop there for today. We'll pick this up on Thursday. Okay. My daughter airdropped that to me. I don't get it. She's supposed to have airdropped it to me. She probably didn't. Okay, see you guys later. Thank you. Thank you very much. I'll be here all week.